Hello, and welcome to this homework help video, where we're going to talk about things related to gravity. We're going to discuss a universal gravitation problem in the first one here. Then we're going to talk about a problem that involves projectile motion, which is two-dimensional, but don't get too worried. We keep it simple cases only. And then we're going to talk about satellite motion, in particular, what are called elliptical satellites, where we use conservation of energy. So let's go ahead and write down some of those key terms, and then we'll get into some key equations. Okay, so for this first one, we have universal gravitation. So universal gravitation, that's going to be the key term that most directly relates to the first problem. For the second problem, the key term would be projectile motion. Projectile motion. And for the third, this would be elliptical orbits. Okay, so put it right here. So elliptical orbits. And additionally, or as a kind of necessary foundational idea, conservation of energy. Okay, so let's go ahead and go to our first problem. Now, you can see the part A, part B, part A, but these are three individual problems, so don't get confused by that. So in this first problem, which we'll go ahead and call problem 1, let's talk about what equation we will need. Well, in this case, they actually give it to you. So this is the only key equation we need. Now, historically, this is a problem that students tend to struggle with, not because of the difficulty in solving it. It falls squarely into the category of a plug and chug problem, but rather I think the difficulty of dealing with scientific notation and correctly entering the values in the calculator. Okay, so let's go ahead and do that. I'm going to make one change. We're going to have our mass for our baby different than stated, but you might wonder what's the baby doing in the problem? So let's go ahead and read it. So find the force of gravity between a newborn baby with a mass of, and let's choose a mass here of, how about 2.15 kilograms, and the planet Mars. All right. And actually, you know what? We can go ahead and switch this one up as well. Let's go ahead and make it, Venus. And in the case of Venus, this is going to be on the order of 10 to the 24. So we have here, let's go ahead and make this, we'll keep this value as 5.0, so actually I am changing it, and then it's going to be times 10 to the 24 kilograms, because Venus is about the same mass as Earth, and so I'm using a value closer to that. And then as far as the distance, we had a distance here of 5.6 times 10 to the 10 from Earth to Mars. I'm not trying to be exactly accurate to the solar system, so we'll go ahead and keep that value the same, although it isn't quite the same distance between Earth to Mars as it is to Earth to Venus. But of course, those distances vary with our respective orbits. So that's just a value that we're going to put in the ballpark of reasonableness. Okay, so with those numbers, it is just a matter of plugging them in. Now, you also have to plug in or correctly identify this right here, this uppercase G. And what is that uppercase G? That is known as the constant of gravity, or the universal constant of gravity. So let's go ahead and denote that with a different color. And so this very special fundamental constant, big G, is always equal to the same value, okay? It's determined experimentally. It has to do with the fundamental nature of the universe, and it is 6.67 times 10 to the negative 11, and then Newton meters squared per kilogram squared, okay? Don't worry about the units. Those are just the units that make sure that we are calculating a force, because this is a force equation, as the F probably gives away, right? So we're going to get something that has newtons when we finally solve for it. And what makes this a plug and chug problem, by the way, is the fact that we don't have to do any algebra. We don't have to move anything around. We're just going to put everything into the equation as written, calculate it, and then get our answer, which I'll do over in the calculator on the left. Okay, so let's go ahead and actually start plugging in those values. But before we do so, I'm going to write them out. Okay, so let's go over here, and we're going to write that our force, I'm going to put a G here, by the way. I like to put big G when I'm using the universal law of gravitation, as opposed to gravitational forces on the surface of a particular world, which would be like Earth, right, where it's m times little g. Remember, little g is about 10 meters per second squared. Very, very different value. And the big deal there is that little g, that's specific to Earth. Sure, super important for everyday human life because that's where humans live on the surface of Earth. But big G, that encompasses the entire universe. It's a much bigger concept than just Earth. All right, so let's plug our numbers in. 6.67, okay, so this is for big G, times 10 to the negative 11 in square meters over square kilograms. All right, and then you can see that in the numerator, we have the product of the masses. So we'd have the newborn mass. So by the way, what we're doing here is we're finding the gravitational tug on the baby from Mars. Now, this is going to be a much smaller tug, of course, or I guess it's Venus, right? Because I changed it from Mars to Venus. But this obviously will be a much smaller tug than Earth, say, pulls on that same baby. That's why we don't notice the pull from other planets, because they are much, much weaker because of that huge distance. And then we'll put in our estimated mass for Venus. So 5 times 10 to the 24 kilograms. And then we divide by the distance squared, okay? So we're using that distance of 5.6 times 10 to the 10 meters. By the way, that could, if you wrote it in everyday language, that would be 56 billion meters. All right. And everything is already in base units for you. So you don't have to convert, say, from kilometers to meters. You can just leave it in meters, and the kilograms are the base unit we want. And so let's put in that 5.6 and then times 10 to the 10 meters. And don't forget to square it. Okay. Very crucial. You can see right there in the equation, it's d squared. D for distance squared. I didn't call attention to this, but m1 would be the mass of the newborn, m2 would be the mass of the planet, in this case Venus. Okay, so now with that written out, we're just going to follow our order of operations and just make sure we use all the correct parentheses, make sure that we have our exponents written correctly, and so on. The key idea there is to, if you're using a traditional calculator, like a scientific calculator, don't be hesitant to use lots of parentheses. You obviously need the correct amount, but your calculator will tell you if you don't, because you don't want to have it calculate the wrong thing, right? You don't want it to multiply when you thought it was an exponent and so on. So using something like Desmos is a great way to go about this. And since your exams will be online, you can always use Desmos. And so it might be a good thing to get used to because you're more likely to be able to check your work, have the equation look like it would when you write it out, and just be able to make less mistakes using something like Desmos, which is what I have open here on the tablet. So let's put in 6.67 times 10 to the negative 11, right? So you can see I got that first bit written all in scientific notation. The notation on Desmos is a dot instead of the cross like you see in typical typed scientific notation. Then we'll go ahead and set up our fraction. Now up top, I'm going to have the 2.15. I'm going to go ahead and start the fraction, but then go back up to the numerator and then multiply by the next mass, which I will go ahead and put in parentheses just for clarity. And that's going to be 5.0 times 10 to the 24. Make sure to close those parentheses, although in this case it would close automatically. I could put parentheses around 2.15 as well, right? But it's, it'd be somewhat redundant. But again, if you just kind of want to be confident, you're not making mistakes. And then crucial, you do need parentheses on this one because you're squaring it. Now, otherwise, if you have it written like a fraction like this, you can just put something in the denominator. But if you're squaring it, then you got to make sure you're squaring that whole quantity and say not just squaring the 10 to the 10 part or just the 5.6 part, for example. Okay, so we'll have our 5.6 times 10 raised to the 10th power. And then, whoops, put a multiplication when I didn't want it. Close the parenthesis, then raised to a power of 2. There we go. So we have a value in newtons, which we'll go ahead and write in as our final answer, of 2.29 times 10 to the negative 7 newtons. So in everyday language, it is 230 billionths of a newton, or you could say it's about a quarter of a millionth of a newton. So small force, especially considering that this baby would experience about 20 newtons of gravitational force from the Earth, right? So tiny, tiny contribution coming from nearby planets. Okay, so enough about gravitational pull between two objects, in this case, a baby and a planet. Now let's talk about projectile motion. So this problem here is all about something sliding off a table where its motion is initially entirely horizontal, and then it's going to fall a vertical distance. So this begs for a picture. So let's give it a little sketch here. We're going to have our tabletop, have some edge here. Doesn't matter how you draw the edge. And then we'll have our object sliding right off it. which is going to be, so the speed of, so if the speed is 3.2 meters per second and the coffee table is 0.44 meters tall, find the distance the coin lands from the base. And it's because in the way it's referring to it, in this problem is because in the previous one, it kind of laid out more of the basics of the problem. And so that's why it sounds like we've already heard of the coin. So let's go ahead and put our coin here. I'm just going to kind of make it look like a long rectangle like so. All right, so that is our coin. Going to fill it in there. Okay, and it's going to be sliding off the edge of the table. When it reaches the side of the table, it's going to have that initial velocity, entirely horizontal, of 3.2 meters per second. But let's go ahead and mix that up. Let's make it 4.9 meters per second. And we're going to make the table be 0.66 meters tall. Okay, and we're going to use our unrounded gravitational acceleration. So pay attention to which one you're told to use. I say that because in a lot of the problems, you're told to use 10 meters per second squared, but here you're using 9.8, right? So it's a slightly more accurate version of gravitational acceleration on Earth. And so right here, this little arrow is going to represent that velocity, right, when the coin slides off the table. All right, so let's just call this V, and that's 4.9. All right, 4.9 meters per second. And then our height we'll put in here. We'll have our height from the edge of the table to the ground. And I didn't draw the ground in there, so I'll make it obvious that this is the ground down here. All right, and that value is 0.66 meters. All right, and the path that the coin's going to take in terms of other key terms is a parabolic path. All right, so essentially half of a parabola, if you can think about what a parabola looks like, right? It's that, steepening curve. And then when it's, some point in that parabolic path, it will hit the ground. It will hit at some angle, but we're not concerned about that. But what we are concerned about is the distance it covers before it hits the ground, okay? So we're asked for, how far will the coin move from the table, right? So it's worded as find the distance the coin lands from the base of the table. So precisely what the problem's asking for is this distance right here. And so how far from the edge? That is going to be our value. We'll go ahead and call that D. All right, so here's the thing about projectile motion. It's two parts. The way to think about it is that what happens in the vertical direction doesn't affect directly what happens in the horizontal direction, nor does what happened in the horizontal direction directly affect what happens in the vertical direction. Rather, we have the reality that when the coin hits the ground, it can't keep moving anymore because it has nowhere else to fall. And so you can think of the ground as being the limiting factor here. So if we can find out how much time the coin spends in the air, then we can just plug that time back into its horizontal velocity and then find out how far it moves in that time. And this is crucial because the acceleration the coin experiences, gravitational acceleration, free fall acceleration, well, it points straight down. It doesn't have a horizontal component, which is to say it doesn't point to the sides. It only points straight down. And that means that there is no effect on the velocity of the coin, the velocity that we know, 4.9 meters per second, from gravity. That value remains unchanged the whole time during the flight. Now, the coin sure picks up speed, but all the speed it picks up is from its vertical motion. So yeah, it's going faster when it hits the ground, but only because it's picked up a certain vertical motion, because initially it had zero vertical motion, right? So what we can be absolutely confident that this 4.9 does not change throughout the entire parabolic path of our projectile. And I call it free fall, and you might think, oh wait, free fall is only straight up and straight down. This is still free fall. It's just free fall we are moving to the side as well, right? But the vertical part is still very much free fall. So we still have that very important reality that G, points straight down, is, that's gravity. And also, in terms of kind of my directions here, I'm going to go ahead and call the downwards directions positive, all right? And then we'll call the direction to the right positive as well. And the key idea there is because that's the only directions we're moving, there's no sense in calling downwards negative because then we got to keep track of that. Instead, we say, hey, that's the way it's going to move, so let's call it positive. All right, so let's find out how much time it spends in the air. So to find out how much time it spends in the air, our first of the two equations we'll need is going to be the equation for constant acceleration motion. Okay, you saw this before in previous problems, previous homework assignments. And this simply states that y equals 1/2 gt squared. Okay, so this is the sometimes called the free fall equation. There's a similar free fall equation for velocity that talks about the fact that velocity increases linearly, but here we have the reality that position is increasing, well, with the square of time. Okay, so it's a key equation that tells us the distance that you've moved with a certain amount of time, t in seconds, of free fall. G, of course, is 9.8 meters per second squared. Right, so then since we know y, it's none other than 0.66 meters, then we can solve for t, because of course we know g as well. All right, and the only other equation we need is a rather simple one. This is the equation of constant velocity, not constant acceleration, constant velocity motion. And this one simply is d equals v times t. So you see then that the process, the actual kind of solution method here, is that we solve for t, right, which does require algebra. So solve for t, and then we plug that t into this equation to find d. So plug in t to find d. And that is what we're asked to find. So let's take a look at the algebra. All right, so over here, the algebra using key equation 1, so algebra for 1, will involve isolating t. So what we have to do is multiply both sides by 2 and divide both sides by g first of all. Okay, so the first step would look like this. We would take our 2 and put it next to the y. That would cancel it out on the right-hand side because 1/2 times 2 is just 1. And we'll divide both sides by g, which of course would get rid of it on the right-hand side. So now we'd have our equation look like this. Now we want to get t by itself, and so all we have to do now is take the square root of both sides. Because if we take the square root of a square, that undoes the square, and we're just left with t. So that means that we get to the point where we have that t is just equal to the square root of 2y over g. Pretty nice, huh? Okay, so let's go ahead and plug that in to find out how much time the coin spends in the air, which is in itself is an interesting question. But of course, then we're going to use that to find how far it moves at constant velocity. All right, so let's take our square root, set it up there, a little button on Desmos, and then 2 times 0.66, because we're the correct units. We don't have to convert from, say, centimeters. If we were told it was 66 centimeters, we'd have to convert to meters, by the way. And then we'll go ahead and divide by g. So you can see that, it looks like it's only dividing the 0.66 by g. It doesn't actually matter. So we can just put that there. With the order of operations, you get the same answer. And then you'll have 0.367. What are the units? Seconds. All right, so that's how much time the coin spends in the air. So now it is simply a matter of taking that time, multiplying it by our constant velocity, and we've got how far it moves, right? Its actual impact distance relative to the edge of the table. Okay, or the base of the table, right? Because the table has that vertical leg. And so that's just going to be our, 4.9. So we'll take our 4.9 meters per second, that unchanging horizontal velocity, because there's no acceleration in the vertical direction. By the way, if there's friction or air resistance or something, then that's not the case. But to a good approximation, we can say that there isn't, right? Just steadily moves in the vertical direction. And then multiply by that 3.67 seconds. And that's it. That's going to be our d value. All right. So since this is such like a long number and I want to get it pretty accurate, one thing you can do is actually save this value as a certain letter. So we'll just go ahead and save this as t, natural choice there. So that way on the next line, I can then just say that I want 4.9 times that t, right? And then it knows what I'm referring to because I saved t as that value. And so then I get 1.79, which would round up because the next number is 8. So it would round up to 1.80 because the 9 rounds up to the next to the 10, which brings the 7 up to 8. So we would get a distance of 1. Oops. All right, undo that. Okay. We get a distance of 1.80 meters. And that's it. That is our answer for our projectile motion problem, taking a time in the vertical direction and using that time to find distance in the horizontal direction. So our last problem, this elliptical orbit conservation of energy problem, is, I think, the easiest. So let's take a quick look at it. So we're asked, rather simple statement, use conservation of energy to find kinetic energy. Well, although the statement of the problem is a little bit longer, it's up here. All right, so what does it tell us? It says, a satellite at a particular point along an elliptical orbit has a gravitational potential energy of 4,700 megajoules. So we have a gravitational potential. I'm going to start writing these down. So I'm going to call this one UG. We often use uppercase U for potential. You could use uppercase P, but we also use that for power, so it's better to use uppercase U for potential. So 4,700. Okay, and what is that M? Well, there's a lot of a particular like power of 10 notations that are used with the metric system, such as C for a hundredth, or lowercase m for a thousandth, and lowercase n for a billionth, and so on. You can easily look these up online. They're also referenced in the textbook. In this case, uppercase M is a mega. That's as I read it, you read it as a megajoule, and it's a million. So it'd be 4,700 times 10 to the 6 joules. Now that's not in proper scientific notation because the decimal place is right here. And in scientific notation, your decimal place always has to be between the first and second digit. But that's the thing about using this type of prefix for powers of 10. And we could convert it over to scientific notation if we wanted to, and we could write it as 4.70 times 10 to the 9 joules. See? So either way, but same value. Now, okay, and it has a kinetic energy of the same amount. So this is going to be our kinetic energy at that point is also 4,700 times 10 to the 6 joules. Okay? And now we're told, so that's at some instant in its orbit, okay? We're told at a later point in its orbit, the satellite's potential energy is now 6,500 megajoules. So it's gained potential energy. What that would look like if we had, say, a green planet like Earth, little circle here, and we had our orbit. Well, our elliptical orbit would look something like this, okay? And then we would have some point, or 2 points along that orbit, where at one point there is an equal amount of kinetic energy and potential energy. So say right here, and this we could call this point 1. So put a 1 on our potential energy value and our kinetic energy value, and right there. And then point 2 is where the potential has gotten bigger. So if we're going in the counterclockwise direction, which is how orbits are in the solar system, as viewed from above, then we're going to get to some point over here, say, right? And this is just an estimate, where we have a point 2, and you see that we are now further from the planet that we're orbiting. Now, a lot of orbits are more circular, but there are plenty of these orbits that are definitely not circular, like the orbits of comets, and this would be such an orbit where there's a significant difference between, the distance between the orbiting body and the orbited body. So, indeed, the distance here, you could call that the radius at point 1, is smaller than the radius at point 2. So we see that at point 2, the orbiting object, the satellite, has gained potential energy, which is exactly what we have here because numerically, 6,500 is bigger than 4,700. Okay, so let's go ahead and write down our value for kinetic energy right over here. So we'll call this K2. All right, actually, that's the one we're trying to find. So I'll put a question mark there. But then we'll put UG2, and that one is going to be our 6,500 times 10 to the 6 joules. Okay, so we know initial, right, potential energy. We know initial kinetic energy, which is to say at point 1, right, because that's our initial point. And we know final potential energy. The only thing we don't know is final kinetic energy. So what does the equation look like to put this all together? Well, the single key equation for conservation of energy as it relates to, elliptical orbits is just this. So key equation is just what I'm about to show you. And I think you'll be happy at the nice simplicity of this equation. So we'd have UG1, so potential at some point 1, plus the kinetic at that point. So the sum of those two energies, that's what is conserved. That sum is called the mechanical energy. So the sum of potential and kinetic is mechanical energy. That's the term given to it. And it doesn't change. If there's no heat loss or anything else, then this system has to conserve that sum of the two types of energy. So that means that by the time we get to point 2, we'd have UG2 plus K2. And we simply solve for the one value we don't know to make sure that this equation is balanced. Right? Because you think you got some scale and you have to keep it balanced. There has to be the same amount of energies. The amount of potential and kinetic varies, but their sum doesn't. Okay? So let's go ahead and put in our numbers here. And you can see that although it was helpful to think about all the megajoules, we could actually just leave it in megajoules rather than converting it to joules because our final answer is going to be in megajoules as well. So we'll go ahead and put on 4,700 here, or 4,700 here. And we'll put that in the 65 for the final or the at point 2 potential. And now we have our single unknown. So again, it's algebra, But in this case, unlike some of the more complicated algebra where you have to, multiply both sides by something, divide both sides by something, even take the square root of both sides of the equation, here all we have to do is just subtract 6,500 from both sides. And I did make one little mistake. I left off my m, so it looks like I was mixing joules and megajoules, which is not correct. So let's put the correct notation in there. All right, and I'm just going to subtract 6,500 megajoules from both sides. And there we have it. We have that the kinetic energy at point 2, the point where the potential energy has gone up to 6,500, is just going to be, oh, what's this one? This would be 80, or 94, right? So 9,400 megajoules, because 4,700 plus 4,700. Let's confirm that I didn't make a arithmetic mistake there. 4,700 plus 4,700, 9,400, right? Of course, times 10 to the 6th is megajoules, but we'll leave it as megajoules. And then minus 6,500 megajoules, and that's going to be our answer. So let's just do that. Minus 6,500. There we go. 2,900 megajoules, and we are done. 2,900 megajoules of kinetic energy at point 2. Okay, well, I hope this homework help video has been helpful. Thank you so much for watching.